Afternoon. It's my great pleasure to start our today's Kharkiv Quantum Seminar. It's a very special event today because it's organized jointly with the Bogolyubov Institute of Theoretical Physics and Kyiv School of Economics. This is because Erik Aurell visits these two institutes, and our Kharkiv Quantum Seminar is now hosted by Kyiv School of Economics, where we are sitting. Professor Aurell is from KTH Royal Institute of Technology. Random Gaussian, pure and extremely high-dimensional quantum states is the title of his today's talk. So before I give the microphone to our today's speaker, I would like to introduce him to you with this one slide of biography. Erik Aurell is a professor of theoretical biological physics at KTH Royal Institute of Technology in Stockholm, where he has worked since 2003 in the Division of Computational Science and Technology. His research spans statistical physics, open quantum systems, quantum thermodynamics, quantum black holes, computational biology, and interference methods in complex systems, so quite broad. Very impressive. Erik Aurell received his PhD from University of Gothenburg in 1989 and subsequently held postdoctoral positions at the Observatoire de Nice and at KTH. He became docent in mathematical physics at Stockholm University in 1995. Before joining KTH as a professor, he worked as a researcher at the Swedish Research Council, lecturer at Stockholm University, and senior researcher at the Swedish Institute of Computer Science. Professor Aurell holds a Doctor Honoris Causa from Bogolyubov Institute for Theoretical Physics and is an external advisor to the Department of Mathematics of Kyiv School of Economics. So, Professor Aurell, the floor is yours. As the sharing, would you please share?
I will do so. Yeah. Make sure I make no mistake.
About 1 hour for the lecture, and then we have the Q&A section.
Okay, and is it okay? Yeah.
No, it's full screen only.
I forgot to say that also today's seminar is special in that way. It's the first hybrid Kharkiv Quantum Seminar. Number 52 or 53, finally, our seminar became hybrid one. Hopefully, we'll continue with nice tradition.
Thank you. It's a great honor to be here. Thank you very much. I'm really touched that so many people actually came to the talk here in real life. It's both an honor and a pleasure. I should say I will also be here at Kyiv School of Economics tomorrow in the afternoon. So I'm giving another talk here, but then I'm free in the afternoon. And I will be at the Bogolyubov Institute on Thursday. We have a seminar organized together with and I will also be here in Kyiv on Friday, so and the beginning of next week. And the plan is that I will visit part of the upcoming conference in Kharkiv at the end of next week. So I've structured this talk as kind of an introduction to problems that we have been working on. And the collaborators will sort of appear as the talk goes on, and I would be very happy to continue the discussion. And so either here at this place in Bogolyubov Institute, and then online it's also very easy to contact me. I will spend some time on the mathematical problem because I realized there's a mathematician coming to the talk. So I will take the mathematical maybe even more. So yeah, the two mathematicians coming to the talk is great. So I have a problem I'm trying to solve, and it looks clean enough that I can state it in 2 slides. So I think it is a bona fide mathematical problem, and I don't know how to solve it. And I think if I could solve it, me and my collaborators would be famous. And so, I mean, I would be happy if you would join me in this endeavor. But it's an overview of, and I will otherwise try to not get into too much in the technical details. Some of them I could be able to do in 1 hour, but not all of them. And also some of the technical details I the very first talk, well, one of the very first talks I gave on this topic was actually at the Bagalubag Institute when I visited the first time. So I covered some of the material and I will basically skip that material in the talk today because it was already covered when I was here in Kiev first time, some years ago.
Eric, excuse me, before you start,
Should I stay like this?
No, you need to share the full screen mode because our more than 50 people in the Zoom audience, they see not what you project on the screen.
No, just stop sharing and share again.
Yes. Please share the presentation in the full
Stop
screen.
share.
Okay.
Do first full screen.
Yeah.
And after that, share again.
Yeah, but then where do I find the sharing now?
To the audience in Zoom, I would like to explain that we have this
and it looks like this to me. I don't know where is the sharing now.
Maybe here, small.
This one? No.
No, this one, this option, where more? The last one.
This one?
We don't see you.
We don't see your screen. Yeah.
So that's my problem.
Standard is a problem, it's not your problem.
Yeah.
What we see on the screen differs from what we see
Yeah.
in Zoom.
Yeah. Okay. So I'll try again. That maybe it works better next time. You know, this is always
No, you should first do full
but
screen.
you are maybe much
Yeah.
faster than me. Maybe you can come.
Then when you
Yeah, sure.
You should stop sharing yours. This.
Okay. And then next one.
Then we go to this. We go to train. Is it okay? And then
But
we resume. Yeah. And I can. Can you see the?
Wait a second. Yes.
now it's
Yeah.
fine.
Yes. Now.
Thank you. Okay. Okay. So I'll first spend some time on the motivational example of this. And we had this problem before. The arrows don't work, but this sorry. That?
No.
touch.
Which one?
It works.
Touch?
It works.
Okay. Look, yours much more. What did you do now? Now I can do? Okay. So the motivation example, and actually the real example that we want to end is related to the Hawking information paradox. So it's related to black holes and Hawking radiation. And just to tell you, now, of course, it's been known a long time that black holes exist in the universe. And that's probably the most important problem of them. And now there are also pictures, or actually visual renderings of pictures of the black hole, of big black holes in some galaxies far away. Then it's also well known that a black hole forms in a gravitational collapse. And this is one of the pictures provided in one of the books by Penrose, who is not only a fantastic mathematician and physicist, but also can draw very well. So he then has this illustration that you have incoming matter, which somehow goes to a very condensed state, usually called singularity, but nobody really knows what it is. And then you have a horizon forming around the black hole, and on this horizon emits radiation. The Hawking radiation is emitted, and eventually, at some time in the future, which is actually very long for an astrophysical black hole, the black hole will have disappeared, and all that remains is Hawking radiation. So the talk is not really about the black hole, if you want to be strict, but about the state of the Hawking radiation, or modes which have the properties like the Hawking radiation when they go away to infinity. So the quantum state of this system, which essentially is photons going away to infinity, but could also be other particles, other low mass particles, essentially. So neutrinos and other matter. And so, since this I expected a broad audience, I included this very kind of pedagogical slide. When you talk about black holes, there are certain units invented more than 100 years ago by Max Planck, which are very useful, and those are units of mass, length, and time that you can construct out of the velocity of light, Planck's constant, and the gravitational constant. And I think we have all heard of those, but if we don't work with these, we don't remember them. But perhaps we remember that the Planck length is extremely small, so 10 to the minus 35 meter. And then the time, which is related by the velocity of light, is of course even smaller. But the Planck mass is not at all small, so it's like 20 micrograms. So it's something that you could see with your naked eye, and you could almost feel it if you have a grain of sand that you would have in your hand. So there's kind of this interesting point. Of course, as a mass of an elementary particle, which is the way it's usually presented in physics, it is a very, very large mass. That compared to to our ordinary life, it's not a very unusual number. So, but these numbers, in terms of these numbers, you can state everything without many quantities. And the Hawking radiation, which comes out, is thermal, according to Hawking. And you only need to remember one number, which is 1/8 pi, because the rest is dimensional. The Planck mass times c squared is an energy. Energy over Boltzmann constant is a temperature. So all the prefactor here is a temperature. And the ratio of the mass of the object, the black hole, to Planck mass is dimensionless. So 1/8 pi is the only number you need to remember there. And for a spherically symmetric black hole, the only number you need to remember is 2, because the radius is twice the Planck length, which is extremely small, but 10 times the ratio of the mass of the object over Planck mass, which for an astrophysical black hole is very, very big. I say 10 to the 30 kilograms for the sun, so 10 to the 30, you get a large number. Okay, so if you have this temperature, there is a formula which is now more than 150 years ago invented by the German physicist Clausius, which relates temperature to a quantity which he also named entropy. First, in the first paper where he introduced it, he called it the equivalence value, equivalence stat. But then he changed later because he had a good nose for publicity also, and he invented the name entropy. And of course, we know this thermodynamic relationship that the partial derivative of the entropy with respect to energy is 1 over the temperature, and from this then you get a temperature which is, an entropy which is with the proportionality constant, and then times the quadratic ratio of the mass of the black hole of Planck mass. And for some of you, this must be well-known things. If you read Hawking's book on the first minutes of the beginning of time, it's well-known for the mathematicians. Maybe you haven't seen this since high school, then you see it again now. Yeah. Okay, and this, of course, is a very unusual entropy. If you are a mathematician with an interest in physical problems, of course you know that entropy is typically an extensive quantity, which is linearly proportional to the mass or to the number of objects. But here we have a quantity called entropy, which is quadratically proportional to mass or to the number of objects in some sense. So it's a very unusual entropy. Now, there is some details that if we are not considering the entropy of the black hole as predicted by Hawking, but the entropy of the radiation having this temperature, is that actually the same radiation, the same entropy? If you count all these modes going off to the infinity with the frequencies as given in Hawking's theory and the temperature. And it turns out not quite. So there is an entropy increase going from the black hole to the Hawking radiation, as found out by the Polish-American physicist Wojciech Zurek in a paper published already now more than 40 years ago. If it's only photons, it's very easy. It's an elementary calculation, so the prefactor is 4/3. If you include other low mass particles like the neutrinos, it's a very non-trivial calculation, which is done by another important player in this field, Don Page, initially more or less at the same time, and there is a review by him in 2005. So the pre-factor is not very different from 430. It depends on which modes you include, but there is some. So you should, maybe that's in the next slide, but I'll say it anyway. So there is the entropy of the object, which forms the black hole, and you would think that the entropy then, from a bowl of gas to something very compact decreases. That would be a normal, maybe a very usual point of view, but in fact, it's not at all the case. And the reason is that this is a super extensive growth. So a quadratic always beats a linear if you're large enough. So in fact, the relation is the object collapses in space, but the entropy increases enormously and then increases a little bit more when the radiation goes away. So if there is somebody who's read these books, maybe I should also say that, of course, this spherically symmetric black hole is a special case of a more general black hole, which can be electrically charged and which can rotate. And in that case, there is an even simpler relation of the entropy in ratio of the area over the Planck length square, which is of course as dimension area, the area of the horizon around the black hole. I prefer actually this more, even though it's a more special case, because it's the one for most black holes, and it accentuates that this is a super extensive relation, which is kind of hidden in this presentation. But of course, it is a special case of this more general one, which you may have heard. So just to get some numbers on what I already said. So if you can Google for what the astrophysicists tell you what is the entropy of the sun today, more or less they know, because they know the temperature, they know the temperature profile of the sun, they know the composition of the sun, and it's a ball of gas, so they can compute a very good approximation of the total entropy of the sun, and it is about 10 to the 35 joules per Kelvin in these units. And then you don't need to ask Google, you can do the calculation in your head using a Hawking formula for the black hole. It's just remembering the mass of the sun and the Planck mass, and you find that it's 10 to the 54 joules per Kelvin. So we have an increase of entropy of which is a factor 10 to the 19 for an object of the size of the sun, and then correspondingly larger if you have even larger black holes. And I will come back to that to the end, but I think this is the number one mystery in the black hole science. Mm-hmm. What is this increase of entropy? What could it possibly be? And it's not a small increase, it's a factor 10 to the 19. Huh? One is 10 to the 9 entropy is 10, one entropy is 10 to the 19 times larger than the other one. But let me, before, at this moment, let me say that, of course, this means that if you have this really large difference in entropy compared to the black hole, what came in, fell into the black hole, whatever formed the black hole, is practically zero entropy. It's 10 to the 19 times smaller. So you could say you have almost what formed the black hole is comparable. If you compare it to the entropy of the black hole, it's like if it's in a pure state, as it has zero entropy. It's so much smaller. So we have a problem which is related to thermalization. How can we have a system which is in a pure state, which has zero entropy, but which nevertheless behaves as if it has a positive entropy, if you know its different parts? And this is a problem, how you can have an isolated system evolves conservatively or unitarily, if you want, in quantum mechanics. And if entropy is small initially, it remains so for all time. That's a statement of conservation of entropy. But still, you have it seems like a isolated large enough system can get close to thermalization. And here we have something similar that we have, and then of course the entropy would be much larger. And this is an old problem in statistical physics, which goes back to Boltzmann, but which in the more recent decades has been, at least on the quantum side, more often discussed in terms of the eigenvalue thermalization hypothesis, which maybe interests some of you. I mean, yeah. It's a major field in condensed matter theory these days. So I will now tell you my problems. That is what this should say here. I mean, it's kind of hidden at the top of the slide, but my problem, of course, it's a little bit different. The problem of the state of the Hawking radiation going off to infinity is not quite the same as thermalization, because once the whatever this radiation has left the neighborhood of the black hole, they are not interacting, so they are just non-interacting things going away to the infinity. And whatever temperature they had when they left the black hole, they will keep for all time, these modes. So it's not really that everything thermalizes, but it's only the separate modes to thermalize. So the questions: is it possible to have a pure total state of the system? For instance, the state of all these modes of Hawking radiation, which we can take to be all modes of phonons disappearing to infinity. And there are some tricks in how you define them, but I will skip that. It's already in Hawking's initial paper to kind of discretize time and consider modes which are actually frequency bands corresponding to time intervals where more or less the temperature can be considered to be the same. So is it possible to have a pure total state? The state of each mode, that means the reduced density matrix of each mode, is thermal with its proper Hawking temperature. That's one class of problem, and that's the first problem that we looked at. And do other properties of such a system behave as in a thermal ensemble? And eventually, and that's what we cannot do, we would like to compute the Page curve. That means the entropy for Neumann entropy of some fraction, say the first half or first quarter or first fraction t of the modes where t goes from 0, then just in the beginning. This is what we can compute when we're just here in the beginning, and in the random ensemble towards the end. Okay, so these are I will tell you a little bit how we did this, what we can say about this, and where we are stuck on this. And of course, there's an enormous recent literature from the high energy side on the Page curve, with many famous names. The literature which we cite partly in our papers is really enormous. And in the last, say, 5-10 years. But I don't think there's any consensus, and especially there's no simple model, simple random model like the one I would like to solve. So here comes a little bit of, I will tell you a little bit about the first paper, which we did together with Paweł Podolecki and Michał Eckstein, now 4 years ago. And so that's the answer to the first question. Can we have a pure total state which has the states of the separate parts as we want them to be, for instance, in Hawking radiation? And this turned out to be a solved problem in continuous variable quantum information theory, which we found by looking at this. So this is an application of results even earlier in quantum information theory, which maybe are known to some of you, or maybe all of you, but I will be happy to share this. It's quite beautiful and very compact results. I will use the same construction as in the second paper, but I will not talk about it since I already did that at the Bogolubov Institute some years ago. It was published 2 years ago. And I will talk about this paper, which I have just gave a brief presentation when we had the meeting in Reef last year, and then it was not yet published, then it was only in a preprint form. So what we can do is the average entanglement entropy of a small subsystem in the same ensemble and the same construct as here. And what we would like to do, what we cannot do, is the average entanglement entropy of any subsystem, which has a size from 0% to 100%. So let me give a little bit on the quantum marginal problem. And let me start by saying that in classical sense, the marginal of a probability distribution, say 2 variables. Yeah, I'm not sure how that can be done. Yeah.
No, you should
no,
put
you
and
should-
wait.
Sorry, Alt maybe?
Alt and wait a bit.
Okay, I'll try.
No. Press and wait a bit.
Press and hold down.
Yeah, hold on. Yeah, wait, yeah. And
Release.
No, doesn't work.
No.
Right.
Okay. So the larger problem in probability theory, just to give a definition which is understandable to everybody, is you have a distribution of two random variables which can take values small x and small y. Big random variables are big X and big Y, and the marginal over X is the probability distribution over random variable X. You get by summing the probability of all the possible values of the random variable Y. This is the marginal problem. And there is one aspect, there are many interesting aspects of the marginal problem in classical probability, but one which is not interesting is a pure classical state, because the margin of a pure classical state, if that a pure classical state is a delta function, so the marginal is a delta function in one dimensional. So it's somewhat interesting. But in quantum, this is an interesting problem because we know that the general bipartite quantum state can be written in a wave function way, in this way, as the sum in a basis. And then this is a pure state. And then the marginals, say, in state A and B are the traces of the in the other part. So the marginal of A is the trace over the other part B in a bipartite state of the pure state written as a rank 1 matrix. Okay, so this is well known. So we have something quite non-trivial in this case, and quantum marginals are typically not pure. Now you can consider the following mathematical problem. Given a pure state of some Hilbert space, given a Hilbert space of some dimensionality, divide that Hilbert space into subspaces, specify a density matrix on each subspace, so the marginal on each subspace. Does there exist a pure state in the full Hilbert space which has these marginals? That's the quantum marginal problem in generality, and it's considered to have been solved by this Ukrainian mathematical physicist who I think for a long time has not worked in Ukraine in a series of papers, and the most well-known is a paper which was never published. It's one of those mathematical papers which for some reason never got further than the archive, but that's considered to be a general solution. But it is actually a very difficult paper to read, and it's not constructed. So it gets, the construction in general gets more and more difficult if you take more and more parts, and if you take more and more possible, so the dimensionality of each part gets larger. There is some more recent literature that attempts to solve this more or less, but better, but it's still difficult. But there is a special case which was found later, which is if you specify that the total state is not only pure but also is Gaussian. And so then we fall in the realm of Gaussian information theory. And so here is some basic definition in Gaussian information theory, which, of course, everything is characterized by a correlation function, which also has a classical meaning as a correlation function. And this correlation function, in ways which are well known and well documented in the literature, is all the input that you need to describe the quantum Gaussian state. Okay, you can have a shift also, but this is not important in this case. Okay, so like any correlation function, a correlation function is a symmetric matrix. You can always symplectically diagonalize it. So you can write it as a symplectic matrix times a diagonal matrix, which is like an eigenvalue matrix, but all the eigenvalues are positive and they are repeated in pairs. And they are then known as symplectic eigenvalues. It's like normal form, normal modes construction in physics of oscillators. And then, of course, you have to have the transpose of the symplectic matrix on the other side. So if you have this, so you have this additional assumption of not only a pure state, but a pure Gaussian state, and all the marginals then, of course, also have to be Gaussian, but typically Gaussian mixed states. Then there is a result now published in 2008 by Jens Eisert and collaborators, which is very easy to state. So you have two sets of numbers. One set of numbers which are the symplectic eigenvalues of the total state, and if they're pure, they're all one, because there is a relation so saying that pure state has the eigenvalues one. Okay, you cannot have less than one, because then you will not satisfy the certain uncertainty relation, which was on the previous slide. Okay, and then you look at the marginals, which are also Gaussian states, and you look at the symplectic eigenvalues of the marginals. You have two series of numbers, D1 to Dn and C1 to Cn, and there's just these majorization relation that has to be satisfied between the C's and the D's, and one additional condition which has to be satisfied for the C's and D's. And this is super easy to satisfy for Hawking radiation, because if you take pure state, they're all ones, and if this one, these are all the these numbers related to the average photons in each mode in Hawking radiation. So 1 plus the average number of photons here. So this is satisfied very easily, all of them. And then here, this one basically says that the last one of these photons in the modes has to be less than the sum of all the previous ones. So the last mode cannot be populated, the ones with most photons cannot be populated than all the sum of all the other modes in Hawking radiation. So this is super easy to satisfy for a large, in fact, I would say probably for any very high dimensional system. So this is a solved problem, and it was just not applied to Hawking radiation before we reworked this pattern. Now, 4 years ago. And so, at least, if you're interested in these properties of the Gaussian marginal problem, this is really the go-to paper, which the reference is in our day. Let me go to the next topic. So we wanted to say more, and so for the second paper, we invented a model of random Gaussian pure states which share all the same marginals. And I should say that there could be different and better and smarter models for random Gaussian states. Of course, since any pure state can be written as the matrix product of a symplectic transformation and its transpose, because for the pure state, the symplectic eigenvalues are 1, so it's just the identity matrix in between. It, of course, goes down to a statement of random symplectic transformations, and there could be other ensembles of random symplectic transformations which are better than the ones we found or that we worked with, but let me state the ones. They are, we take the flat measure on all quadratic matrices, and then we enforce the constraint that they are symplectic, and then we enforce the constraints that each of the marginals are as they should be according to, for the application, the Hawking radiation or something else. So there is one big constraint for simplicity, and then a set of smaller constraints for the marginals. So you could say, okay, is this a normalizable measure? That would be a mathematical problem, mathematical question. Yes, it is, if we give conditions for all the marginals. If we don't have these conditional marginals, it's of course not good to normalizable measure. So this is the measure that maybe is the most stupid physicist random model one could think of. Maybe there are others that are better. Use the group structure or select the group in another way. This is the one that we use. Okay. And then we could say that in this ensemble of pure random Gaussian state, we can compute any property we like, at least in principle, by taking the average in this ensemble. The average would be TS, and then this, of course, implies some measure here. Okay, and the measure is, yeah, this is the way of writing the measure by enforcing the constraints and then having a normalization. Okay. And I will skip over what we did in the second paper where we considered mode correlations in this random model, which can be done quite exhaustively, I would say. You can compute what they are, you can compute if two modes are entangled or not, and by using different tricks. And I will instead focus on what we did here, even though that in the third paper, even though that requires us to jump a little bit. Okay, so now let's suppose that eventually we're interested in the average for Neumann entropy. For Neumann entropy is mine, so it's a log rho log rho, trace log rho, it's a Neumann entropy, and we would like to average this in this random ensemble. So usually it's not easy to average a log, so no problem. It's easier to average something to a power. So suppose we can average rho to some power, which in this business is usually written x. And if we can do that for x equals 1, 2, 3, or 3, and if this is an analytic function and then equal to 1, we can take the derivative, and this is the way in which we can get the average for Neumann entropy. And the for Neumann entropy of a subsystem is, of course, the entanglement of the subsystem. Yeah, subsystem. That's the meaning of this in quantum information. So here that's the road where we're going, and the start of this road is to consider the well, of course, the trace. The trace of rho to power 1 is of course always 1, so that's not a constraint on anything. But the trace of rho to power 2 has a name. It's called the purity of a quantum state. And for a Gaussian state, it's well known that the trace of a Gaussian state with a given correlation matrix CA is by some tricks 1 over the square root of the term. It's a known result. Okay, so for quantum states. So then we can say, okay, so now we have this purity or the trace of rho squared, and we would like to say, can we compute in this ensemble that we have the average of average purity? And as usual, one invents a trick so that this thing here is represented by a Gaussian as the integral by a Gaussian. So that's the first term here, which you can perhaps not see very well if you're online, but at least the people in the room can see what I'm pointing to, where I mark. And then the constraints are represented by Fourier variables. So then you introduce some new variables, B, to enforce the symplecticity constraint. And since the symplectic condition says that the symplectic form is preserved by the symplectic transformation. So the symplectic form is antisymmetric. So the matrix which enforces this constraint is also antisymmetric. So B is a full antisymmetric matrix again, which we integrate over. That's the space you integrate over this. While the constraints over the marginals, they say that if I take the marginal in the state given by the symplectic matrix S is S transpose, and that should be equal to something that I know, which in Hawking theory would be the correlation function of the separate modes in Hawking radiation. So that's one constraint for each mode. Oh, you could make it a little bit more general. You could take a block of modes. So that's one constraint for a mode or a block of mode. And so you have one block matrix A, which should be introduced. So this matrix A is symmetric because this is a symmetric thing, but it has a block diagonal structure, or in the special case, it has a mode by mode diagonal structure. So these are A and B are two quite different matrix Fourier variables, one full matrix, antisymmetric, and the other one symmetric, but not at all full, that's these blocks. And then you can integrate, then everything is Gaussian, and you can of course integrate out the matrix integral over S, and you have instead an expression as a ratio of two determinants, which now depend integrated over R, A, and B. And these determinants, the one in the numerator is, as you can easily see, of the form here, that this is a perturbation of this one. In fact, it's a rank 1 perturbation of this one. So you can guess, and it's also true, that you can, at least in a limit, when a certain limit, which I will not state explicitly now, but we can discuss, you can evaluate this ratio and you get this very simple result. And that comes on the next slide. So by some tricks, which I will skip here, and I will be happy to discuss, you will end up by finding that the average purity of the state reduced to subsystem A in this ensemble is the same as the purity of a Gaussian state, mixed state, on the same subsystem A, having the correlation matrix, which is the constraint correlation matrix. And this, the main assumption of getting here is the assumption that you can treat this. The trick is to use this rank 1 perturbation, and eventually you have a small. You have to assume that the support of this vector R represents the subsystem A has much smaller dimensionality than the full subsystem. And this trick you can also do. Oh,
I'm sorry.
maybe we should check.
Stay to the nearest shelter.
Yeah,
Sorry for the loud.
yeah, maybe we should find out what it is, if we need to go to the shelter or not. Somebody should.
There is a shahed in the direction of Brovary.
Увага!
Окей, провори спорове.
Негайно вийти до укриття. Поки не користуватись сходами. Дбайте про свою безпеку і залишайтесь в укритті до оголошення відбою тривоги.
The broker is quite far from here, no?
Airway alert! Please proceed to the shelter immediately and use the stairs. Take care of your safety and stay in the shelter until the end of the alert is announced.
So, yeah, Mr. Chairman, you decide. Should I?
Yes, please continue. I'm from
Gordon, you should probably explain. We are found the right bank on the.
I need first Brovary.
Yes,
Yeah.
okay,
Yeah.
okay.
It's far away from.
Yeah.
It's провори, it's
Yeah.
far away, yeah.
Okay, good. So we can do with the, so I guess this trick was well known for at least a specialist for the purity, but there's also a higher purity. If you take x larger than 2, you can use tricks of, well, I wouldn't say tricks, it's basically very elementary properties of quantum coherent states, and to have a very similar representation to the Gaussian representation of purity. You just have a more complicated thing that you integrate over. So for basically for x equals 2, which is purity, you have a rank 1 perturbation, and for any greater than x, you have a rank x minus 1 perturbation. And it's so basically you're integrating some other quadratic functional, which collects up the different numbers of actually x minus 1s of these r's in a particular way, which is given by this coherent state representation. And you can collect all these r's into one big value v, and when you take this value v, you will find eventually this result. So is it exactly the same as before, only x can be any positive number, from 1 up to infinity, any positive natural number. So here then we have this kind of, this called the replica trick in statistical physics. We can now say, okay, we have a very simple formula eventually, and then we can analytically continue this to x equal to 1, and we can take the derivative, and then we have the the average von Neumann entropy of the reduced state in a small substate A is the same as the von Neumann entropy of the Gaussian mixed state on that, which is given by the constraint matrix C hat A on that same subsystem. And there are some analytical tricks going here. I mean, going up to here, from here, so the standard application of the replicate calculation. Okay, so this is what we managed to do, and there is this assumption that the dimensionality of the small subsystem has to be much less than the total dimensionality. Otherwise, we cannot do the calculation. And so now I told you the result that we have, and now I'm going to tell you the result we don't have. And the result we don't have is kind of what's behind. I'm going to go a little bit behind, open the hood in what kind of considerations actually led to these equations, at least how we like to present them now, and that they naturally lead to a problem involving symplectic transformations that look simple enough. At least it can be stated in 2 pages mathematically, 2 slides. So hopefully it doesn't look too unnatural even to our mathematical friends. Okay. And of course, I asked friends, and these are the only friends who wanted to talk to me about this in Stockholm. But they said nothing useful at all. And I also would say that generally I lost a lot of time talking to them. They were not so helpful.
So they are not really good friends.
Indeed, they are not. Now, maybe they have learned from me, but since I don't know the answer, they cannot learn any useful. But they maybe learned that there's somebody looking for these problems. So I'll tell you a little bit about these, about the mathematics here. So one thing is so it's about variational equations, by mean field and variational equations. And so there are 2 matrix variables which we have to solve by variational equations, by mean field, B and A. And just to repeat, B is a full matrix but antisymmetric, and A is a block diagonal symmetric matrix. And it turns out that the variational equation for B, which is from one of the formulas in the previous slides, it is a bona fide matrix equation. It's the inverse of something minus the transpose of that something, inverse of that something, so that this the left-hand side is an antisymmetric quantity, and this is equal to the symplectic form. That's the variational equation. And you can turn this around to say, okay, I can take out, since B here, and so B is antisymmetric, that's why B here stands and minus B. Okay, it's a transpose. So I can take everything else outside, and I call this, it's a symmetric part, so it's a symmetric plus antisymmetric minus 1 over symmetric minus antisymmetric. And I can take out the square root of the symmetric part before and after, and I have a new quantity here, B tilde. And this B tilde, I can take the square root, which I take out, I can put it on the right-hand side. So I have a relation between a second equation B tilde, a second quantity B tilde, and a third quantity D. And the quantity D is one of these forms of, it's not quite called the Hamiltonian matrix associated to the symmetric matrix, but very close to it. So this is a matrix which has the eigenvalues the same as the symplectic eigenvalues of this, but plus minus. Right? So this is the, so, and there's, this can be turned around to this equation here. And so this is a matrix equation between B tilde and D, or in fact, inverse of D. And so this they compute so that you can solve them in a common basis. And there's only one solution, or only one class of solution, which preserves that B is antisymmetric. So it looks like this. So here, these are the eigenvectors of the matrix D. So they are related to the symplectic eigenvalues of the matrix C. Okay, and here we have the lambda k are the eigenvalues, or the symplectic eigenvalues of C. So you have the B tilde is related to this, and there's another formula for B, which is written directly in terms of it's some other things. It's in the eventually will be in the paper. So and then I will skip y, but I'm quite sure that all these signs, in principle, I have n signs, one sign for each mode, but I'm sure that the only reasonable solution is that all these signs are negative. Let me say that this is so. I mean, and all the special cases that we can solve are like that. So in that case, we have a general solution for B, and so it means that I can now say there is a matrix C, which, if you remember, is back one stage. What is C? C is these Fourier matrix block diagonal symmetric variables A, and there is this rank 1 perturbation given by one vector R. Okay, so these is block diagonal, and this has the same scope as the vector R. And if there is, for the higher purity, it will be, for order X purity, X being 3, 4, and so on, it will be Q minus 1, X minus 1 vectors that are in this. So this is another quadratic form, but a little bit different. But it's basically, this is not block diagonal, this is block diagonal, and this is symmetric matrix C. And so a symmetric matrix C, I can write it as symplectic transformation times diagonal times symplectic transpose. And so my first condition, the first one I want to present to mathematicians, is kind of now the definition of diagonal blocks of this combination here, which is the matrix C, are the same as this low rank, let's say, rank 1 perturbation. Because, so the difference, if I take the off diagonal elements, is 0. That's my first definition. So remember, S, D, S transpose, and minus low rank of diagonal is 0. So it's easy enough to remember. But the other equation, this is the other variational equation for A, so it doesn't have a minus, it has a plus, but it's a plus B and minus B. So it's symmetric. And here is the constraint matrix on the right-hand side. So there's for each block that I have constraint, there is one such equation. This is not one equation, it's a set of equations. So the proper matrix equation, because B has another size and so on. But you can turn it around to say that all the diagonal blocks of this equation is equivalent to this one, saying that ST d prime, and I will get to d prime in a moment, S, the transpose of S d prime S minus the constraint in the diagonals is equal to 0. Okay, so what is d prime? D prime is essentially 1 over d, but not quite. Here's the exact relation. And it's, of course, related somehow. I mean, it comes from the same. It essentially comes from the same reasoning as this one. And it's basically more or less the same as statement. So here I have the two equations which I can put together in 2 slides. And if I can solve these equations, I am sure that it will be easy to solve everything, and the Page curve would come out, and it will be beautiful random Gaussian model, which could be a clean and very easy model for Hawking radiation, and how you can have a pure state which is not only can have thermal marginals, but precisely these marginals and precisely this expected entanglement entropy of the first half or first part of the radiation. So one of them is the off diagonal one, so it involved a combination. So the unknowns would be S and D. D prime is a function of D, essentially 1 over D. And the knowns would be the off diagonal low rank perturbation and the diagonal constraints. But here the condition is in the other direction. So transport S, and it's not D is D prime, and it's S. So if anybody's interested in this problem, I'm very, very interested. Okay. I think I'm kind of towards the end, right? So let me end on some kind of semi-philosophical and semi-physical points after having presented where I'm stuck, if that's okay.
Very nice.
Okay, so semi-philosophical problem. I think any problem should, on a related Hawking radiation, should at least state Hawking paradox. What is it? One way of stating it, and when was it published? So, and I basically said it already, but let me say it again. So one way of saying it is you take a large piece of matter in a pure quantum state, you let gravity act, it becomes a black hole. If black holes evaporates through Hawking radiation, and in the end, all that remains is thermal radiation escaping to infinity. So it seems like a pure state has developed into a mixed state. And that this is an issue was pointed out in this famous paper by Hawking just 2 years after he found Hawking radiation in 1976. And in the almost semi-infinite literature on this problem, you have one possibility is to say actually information, and that means then quantum mechanics is broken inside the black hole. That was for a long time Hawking's own position, and changed his mind towards the end of his life. There's a very strange to outsiders theories on strange physics at the horizon, which somehow I would interpret saying that there is actually no real black hole. And then remnants is another version of this. And then there's the other one, which there's the green one, the green shaded one here is to say that, well, everything should be explainable in quantum information theory. And so that will then be information return in Hawking radiation. And, paradox. I was looking at what is a paradox, and if you look at English, not my native language, but some language we all use, if you want a really strong definition in English, you should probably look at Samuel Johnson's dictionary from the 18th century. And he says, a tenant contrary to received opinion, an assertion contrary to appearance, a position in appearance absurd. And then if you look further, you see that actually kind of in Aristotle, in the prior analytics, has a kind of discussion along these lines. So there's a nice, usually quoted passage which says that, sometimes it happens that we're deceived as in the positions of terms, that means how we have defined the problems. So also deception arises as to opinions, and slightly later, he has a formula which can be exactly adapted. So by universal knowledge, which would be quantum mechanics, we observe particulars, which would be quantum black holes, but we do not know them by particular knowledge, which we could say an accepted and tested theory of quantum gravity, so hence we may be deceived by them. And this would be, you could claim that Aristotle in prior analytics gave the correct solution to that paradox, which I think is quite nice. It's really an interesting book. For somebody who doesn't have a classical education like me, once you sit down and actually try to read it, what a clever man. What a clever man. And now also I end on if I will call it it's a physical problem. I call it semi-physical problem. So I come back to this one, it's if Hawking entropy is actually an entropy, as we understand entropy in statistical mechanics, it should be the logarithm of the available phase space. And what you cannot see here, but it's that it should of course say that S is equal to log n, which is the famous formula due to Boltzmann. And so then the question is, what is this n open by gravitational collapse? If you want to give numbers, okay, so you have a phase space volume before the collapse, call it n, and it increases if you're going to have an entropy which grows by a factor 10 to 9. It means that the phase space volume must increase from n to 10 to the 19. What is this phase space increase? What kind of possibilities are open to the universe? And so there's this very nice review published already 16 years ago which gives a tabulation of the entropies of the different constituents in the universe. So stars, clouds, planets, cosmic black body radiation, small black holes, big galactic black holes, and it turns out that almost all the entropy of the universe today is in the form of entropy of galaxy-sized black holes of millions or more sun masses. So it seems like we don't know what is happening in the overwhelmingly large part of the phase space which is open to the universe. There also you can find some very ancient ideas about this. So there's this wonderful statement that was used by Philip Glass in the beginning of his opera. Open are the double doors of the horizon, unlocked are its bolts, which is the opening words of this opera. And it's actually taken from the pharaoh of this otherwise rather unknown pharaoh at the end of the old kingdom in Egypt. And I found this beautiful picture of something open here. So with this, thank you. And thanks all of you for being a patient audience. And to Pavel and Michał, with whom I started it, and then when Mario Kieberg and Lukas Fackel will join for the second paper, and also were on the third paper together with me, and Robert Johnson was in the second paper. And unfortunately, I've been left without such clever collaborators in the last part, so that's the reason I need more. Thank you. Let's see.
Thank you, Professor Aurell. Now, questions.
So 1 hour, so it was probably okay. Maybe a little bit too long.
Very nice. We are not
It's perfect.
limited. Now it's time for questions and comments from Zoom audience. From here.
Yeah, maybe I do ask. Erik, thank you very much for your talk. It was very clear, by the way, and for me especially impressive that Gaussian states are not only in quantum optics, but it's for such serious problems like in astrophysics. But I see, because people here also see, because quantum opticians, well, we have quantum opticians here who see maybe some parallels with quantum optics with what we are doing. Just direct parallel. But my question is now. Quantum optics, after years of doing with Gaussian states, we arrived to the conclusions that Gaussian states are not really good to realize some really deep physics, and we should go to non-Gaussianity. Here is a guy who is doing very deeply with non-Gaussianity, for example. Who is now collaborating with a group who is doing this. Is it possible that in all this black hole business, so Gaussianity does not work also, so that you, for correct description and to solve it paradox, you need to account non-Gaussianity?
Yeah, absolutely, it's possible. And if you, the logic of I hope my presentation, but at least of the papers, is that we introduced Gaussianity as a constraint on the model with which we can do more calculation. So you could have imagined that we could have, continued with the quantum modular problem of Klatchko. The problem was that none of us could understand the paper of Klatchko, and
but it exists.
It exists, and we don't know how to use it. But of course, Gaussian quantum state or Gaussian pure quantum state is just a small subset of all pure states. So you can sure do more than this. Then there is a large speculative theory, some of this which I cited at least indirectly, on what would be the state of black holes. There are many, but it's all built on Hawking radiation as being the solid foundation that they all believe in. I guess everybody believes that this is what one needs to explain. So you could say that what we did not yet completely successfully manage to do is to explain all that can explain by a simple random model. Yeah, and I'm not sure it will get easier if you relax the conditional Gaussian, because Gaussianity gives extra power. Yeah.
But when I was gonna,
Yeah,
sure. Another question, but if we have such, for example, analogy between black hole and quantum optics, yeah, so maybe it's possible when you have some very, very strange or complicated problem, maybe like this, you know, in black hole, you can go to lab, show this to experimental people from quantum optics,
Yeah,
and to say them, look here, I have such a problem. You can model it with your devices,
yes,
and maybe to measure something after that. This will be like something like a non-universal quantum computer, yeah,
no.
which could, okay, maybe it's classical, but I don't know which one. But and this could model your situation. Is it possible, or is it stupid?
Yeah, no. I think it is. It would be quite possible. Yeah, to say.
Just to reformulate the same things in optical. Let's before it previous you.
And
Увага! Відбій повітряної тривоги. І нехай прибуде з вами сила.
Okay.
Attention! The air alert is over. May the force be with you.
Okay.
Yeah, forest with us, so we can perform.
Very good. Yeah. I given the talk at least once in Stockholm, several, no more than once, I think, but I didn't manage to interest the quantum optics people. There are quite good ones, but they have other problems. Yeah. Well, I mean, what would that mean? It would mean, can you generate such a pure Gaussian states with the given marginals? So this is a kind of problem. And then can you estimate? Well, you can surely estimate, I guess, by the tomography. You can estimate the pair correlation functions. There we have a prediction in the second paper, which I didn't go into now, that how big they are, how large they are. So I mean, this can be tested in the lab for sure. Then I think the phonoid, the entangled entropy, I guess, is more difficult. So you need to have a complete, more or less complete tomography. I mean, it's not really something that I would know off the hand. So I mean, maybe that's the more difficult for the experimentalists. But the pair correlation functions, and where we have the I didn't show them now, but where we have the predictions, that should be doable, I guess. I mean, it should be doable.
Yeah,
I mean, it's a restricted quantum tomography problem.
Yeah, but I believe that such a situation could be very interesting because such an approach could be interesting because some problems are hardly solvable mathematical and if they principle solved, but hardly solvable mathematical. But we can use lab to solve them. Yeah, but why not?
Yes.
With simulations,
Then if you can also, but I think that it's a little more thought if we would, but I mean, that's why I'm here giving this talk. I mean, that's why I chose to give this talk here. But if we could, find a realization of the lab that corresponds to this, I mean, this doesn't then any small rank perturbation, I think would be nice. I mean, to know how to solve. If we can have a lab implementation of this together with that, I think this will really, I mean, but that I think needs a little bit discussion.
Yeah, that's one thing how to do it.
Yeah, but that would be really nice if I don't know how to do it mathematically.
More questions in the Zoom audience? Yes, Gleb Skorobogatka, please.
Okay. Can it be that such entropy burst due to Hawking radiation can be because of problems with definition of density matrix of Hawking radiation state, meaning normalization of density matrix, for example?
I don't think so. Of course, Hawking radiation is a complicated topic if you look at the original paper, but and in the following literature even more so. But if you if you take that to be granted and to be correctly done by the cosmologist and the astrophysicist, what is in the end, what comes out is just a multiphotonic state, not more complicated than any other multiphotonic state. In fact, it was well described this morning by Andrei in his talk to the cybernetics guys, that you have a lot of freedom in the quantum state of photons, and it's like that, So I do not think that this is a problem or that it solves my problem. No.
But
I hope it was a clear
it's
answer.
it's
No.
yet haven't been detected.
No. Of course, we have an issue that Hawking radiation has not been detected and probably never will be detected because the temperatures are so low. So the number of photons, it's so the whole field is not built on experimental numbers, and those experimental numbers will probably never ever come in the real world. But it's built on basically the whole framework of quantum field theory. If you would have that quantum radiation would not exist, you would really have to change something and not change something in quantum gravity, because the original calculation of Hawking, which is still the main one, doesn't really involve anything except propagation of ordinary quantum fields in a background, in a curved space, classical curved space background, which happens to be the one of black holes. So you would really have to change something about quantum mechanics if you are not going to believe in Hawking radiation.
The firewall, the existence of firewall problem shows that there are problems with the connecting general relativity and quantum field theory. So, meaning some questions should be put in the very stage of formation of Hawking radiation. I mean, it's not axiomatically firm.
So the firewall is kind of one sub-branches of this literature, which in itself is quite large. And I'm not an expert on that one. You may well be, and in that case, your opinion is better than mine. Okay, but I do not think that the firewall theory but if it's going to contradict the existence of Hawking radiation, it must be that the firewall kind of extends outside the black hole, that there's something physically happens to the horizon that makes it a difference than just more or less empty but curved space where quantum modes are propagating, which is, of course, the assumption underlying Hawking's calculation. And I think this will be, maybe not yet, but it could well be an experimentally, a problem which can be addressed experimentally. Already now we have pictures, or at least visualizations of optical data on black holes. So we know more or less what they look like. And if the firewall was much larger than the horizon, say a factor, I think should be a factor like 3 to 5, I think one should already see effects in the observational data that we have now, like the one which I showed in the first slide. And I don't think it's absurd to believe that with the improved data treatment and data collection in a couple of decades or so, astronomers would maybe be able to limit the possibility of firewall to be very thick. So I think this is not now, maybe, but in a few years, this could be an experimentally, observationally decidable question.
But this is an open question.
A really convincing argument. Why shouldn't the horizon be as one learns in, I was about to say grade school, but very early, you have the feeling that you have Einstein. In relativity, you're supposed not to feel the difference. You're just falling in the gravitational field. And then you should not feel anything special when you pass through the horizon. But of course, the firewall story assumes that something very different happens at the horizon. Yeah, maybe it's a question of taste what you prefer in this which hypothesis you prefer in this direction.
I would say this is an open problem in its fundamentals.
Which of them is not an open problem?
The firewall problem, Hawking radiation problem, and it will be closed, then it will be experimentally confirmed.
I'm just showing you.
Yeah, but I didn't
Yeah,
understand.
because-
Maybe you can say, did he say that it is not a solved problem or that it is a solved problem? Is it not a solved problem?
It's an open problem.
Yeah, okay, it's an open problem.
yeah.
And then, like many of these open problems, it's a question of taste if you believe it's a problem or not. And I think that the community is divided. So there are some people who think that actually it is not a problem, it cannot be like this. The other problem is to explain how is it possible to have such a large entropy inside a black hole. And I belong more to that side. But of course, since we don't really know how it is, then of course it could be that the firewall is the problem. Yeah.
Well, I do not see more questions. No? Then with this, I would like to close our today's seminar. Thank you so much, Professor Aurell.
Thank you.
It's our great pleasure.
Definitely.
Everybody in the audience, see you at the Kharkiv Quantum Seminar in 2 weeks. Bye-bye.
Mhm.
So now I'm still doing my sabotage.